Welcome back, everyone. So last time we finished the part on the continuous Fourier transform, more or less, and we are now moving towards Fourier series and a discrete Fourier transform. And one tool that we will need for this is the so-called orthogonal expansion. And in a nutshell, the idea is to represent our objects, our functions, our images, like as linear combination of some bases. And these basis elements we call EI, but we don't look at arbitrary bases. We look at orthonormal bases. So that means the elements each have length 1 and they are orthogonal to each other. Yeah, that's what this notation here, that's the scalar product of EI and EJ, is the Dirac delta of I and J encodes. And in finite dimensions, it's very easy to think of examples. Just think about the canonical basis in Rn. Yeah, and a 1 at entry I and 0 everywhere else. So that's very simple and fulfills these conditions. But if you think about function spaces or about images, so you can't just take your image and put like a 1 at one position and everything else is 0, as long as you don't discretize. Yeah, so we have to look at different functions, and these complex exponentials that we had in the Fourier transform, yeah, where we have seen with the frequency representation that functions are represented as weighted integral of these complex exponentials. This is some kind of representation with respect to these complex exponentials. So those will later take the role of these EI. But we will have to work on this to see how exactly we have to fill it in there. But before we do this, I first like to tell you more about this notion. So what we can already deduce from this little structure. Yeah, because at the moment we don't have much structure. We have a vector space and a scalar product, not much more. And another thing that we can look at is the scalar product of any element with respect to an element of our orthonormal system. Yeah, this gives us one real or complex number, and this will be the Fourier coefficients, and we will see soon why. And we already had a first non-trivial example of such an orthonormal system. If we look at the interval 0 pi, so think about signals, signals of finite length in the interval 0 pi, then sine nx is exactly such an orthonormal system, at least after scaling with square root of 2 pi. And what I hinted last time already is, even though we now know that these sine and x are orthogonal to each other, we don't know if they are sufficient to represent everything as a sum or a series of these sine and x. And in the following, we want to study what does it mean for such an orthonormal system to be something like a basis. And the first tool on the way to understand this is the so-called best approximation by Fourier coefficients. Yeah, so these coefficients, the scalar products of something that we want to represent with our elements of the orthonormal system. And so we have the usual setting of this section. So we have a vector space with scalar product X, in short called pre-Hilbert space. We have some number K, and we have a finite orthonormal system. So that's E ends where n ranges from 1 to k. Yeah, so k elements that are orthogonal to each other and have norm 1. Yeah, this is if we take this definition here and use k as n. Or no, n is the just the numbers from 1 to k. This normal case n. Not these are the natural numbers, and this is just a subset, and the numbers 1 to k here are now our index set. So, and now we come to the actual statement. So we look at one element x and some coefficients, yeah, either real or complex, depending on what x is. And the first statement says something about the difference of x to the sum of these orthonormal elements scaled by the Fourier coefficients. So it tells us how well does this finite linear combination approximate our starting object. And what this difference is, it is the norm of x minus the size of the coefficients. Sorry? No. xk is the Fourier coefficient. The dk's come in part 2. So this is when I take exactly the scalar product of the x that we have with ek. So this is like the projection of x onto these directions, if you want to think geometrically. So in here we see that we can quantify exactly what the error is by looking at the norm of the element that we want to represent and the size of the coefficients that we have. And this, of course, has certain implications. Since this here is never negative, obviously, it's a norm. This means that this sum must always be lower or equal to the norm, for instance. But we'll come to that. This is for now just a representation of the difference. The second part now has a C case. So it looks at exactly the same object, but instead of taking the Fourier coefficients, I replace them now with any arbitrary coefficient. So just to be able to compare what is different if I use other coefficients. And it turns out that this is all of that plus an extra term, which is the difference of these ck to the xk. And yeah, if you now look at the meaning of this formula, we can immediately see that the right-hand side is smallest if I choose CK how. Yeah. So that means the error here in this difference of the linear combination to our element, it's minimal if we use exactly the Fourier coefficients. So in this case, in this sense, the Fourier coefficients give us the best approximation of any element x. Yeah, if we choose any different coefficients, we will have a larger error. Yeah, now we just have to prove this. And yeah, since we don't have much structure to work with, the proof is actually rather simple, I would say. So it's just a little bit of computation with scalar product properties and this orthogonality. So I will do the number 1 first. And we will omit the index x. Yeah, so I will not always write norm x and scalar product x because it's always x. So we can just skip this by agreeing that I always mean the x scalar product and the x norm. Okay, so let's now just start here on the left-hand side. And yeah, I want to somehow quantify this. And essentially the only thing that I know is the scalar product of these elements of our orthonormal system. So how could I start rewriting this squared norm to make use that I know something about the scalar product? Yeah, so if you think about vector, this is if you would have the norm of a complex vector, then you would have the conjugated vector. Here's just the scalar product. So we don't know what exactly the scalar product is, but it's exactly the same idea. So we have the scalar product of the of this object here with itself. Yeah, and for your special case of a scalar product, you would end up exactly with the convex conjugate times the scalar product encodes this. So let me finish the line. Yeah, so any object that fulfills the scalar product conditions will have to do some convex conjugation here with the second argument. So for instance, if here we would plug in functions, it would be the, so if this would be the L2, we would have integral of this function times the conjugate of that function, for instance. But since we don't spill out what exactly the scalar product is, we don't see it here. Yeah. No, so we know we have given x, we are given the e's, so that we know what the xk is. Our quest is to figure out what the size of this is. Here. So we want to see that it's just the difference of the norm of the vector to, or the norm of the function to the sum of the coefficients. Yes. No, we usually know what, or we construct EKs in such a way that they have this property and the other properties that we don't know yet, which will make it the basis. Yeah, but we will construct the EKs, and essentially it will be these complex exponentials with the right scaling factor and the right factor in the exponential. But it will be essentially e to the INX. Yeah, you're welcome. Okay, and now we use linearity of the scalar product, or the bilinearity of the scalar product, to further rephrase this. So we get x times x minus this times x and minus this times this sum, which gives us a plus. So this is x with x minus sum k from 1 to capital K, x, k, e, k, x minus x. Here we have the sum, x, k, e, k, plus more sums. And here I now rename this from K to L, because I want to now further use the linearity and factor out the sums. Yeah, and I need to rename them because otherwise I would have two sums over K, and this would be different case. So let's further continue this. Yeah, the scalar product of x with itself is just the norm squared. Yeah, now we can factor out the sum and the coefficients. So that's ekx minus, and again we factor out the coefficients, and here we have to recall that this is a scalar product on the complex values. So if we factor out a linear factor in the second argument, it is conjugated. Yeah, that is always the case for scalar products on complex vector spaces. And here we do the same thing for both sums. So we have xk, and now we have the xl conjugated because it comes from the second argument. We have ek and we have el. So what is this? Yes, exactly. This is xk conjugate, because x comma ek is xk, and if you flip the arguments, you have to conjugate exactly. And similarly, this is xk, and this is delta ij. And now we see, since this is delta ij, the orthonormality, this is only, no, not ij, kl. kl, of course. So this is one if and only if k equals to L. So that means this sum here simplifies. So this double sum is just a single sum. So let's collect all that. Let's collect all the sums. So the product of xk and xk conjugated is the norm of xk squared. Yeah, it's a complex value. Oh, and I wrongly put a plus here. So, so we have another sum. Xk conjugated times xk. Again, this is the norm, yeah, or the absolute complex absolute value of this coefficient. And the last one, as I said, L has to be equal to k, otherwise this is 0. And if L is k, we have norm x squared here again. And we can see that these two are the same. And what remains is exactly what I have claimed. Yeah, so actually very simple computation. I would claim to go from here to here to see that the difference of these two objects is just the difference of the norm square, which I forgot here, the square, and the sum of the squares of the coefficients. Okay, that means we just have to show number 2. Of course, unless there are any questions regarding this part. So let's let's try to compute this. And you see that we need to get in the x case somehow. Yeah, otherwise we will never end up with the right-hand side that we are looking for. So the first thing that we will do is we insert these xk. So here I'm adding them. And I'm subtracting. No, here first I'm subtracting, then I'm adding them back. Yeah, and then that means this part here cancels exactly that part. But we are already approaching like this structure. Okay, and now we have to compute this. And I want to reuse that we already know what this part is. Yeah, and actually this part is what we have here. So how do we do that? Let's make this a little shorter. So I call this capital Y and this capital Z. And now I can again multiply out. So first represent this as, of course, a scalar product x plus z, y plus z with y plus z. And now I'm factoring out exactly like I did here. So this is y plus y z plus yz conjugated. So it would be zy, but I'm reordering immediately so I get the conjugated part. And that's that. Yeah, and